Hello, I am AdityaOjas Sharma of Department of Biotechnology, batch of 2020 B.Tech IIT Roorkee. In my final year 2019-2020, I got this opportunity to work under the supervision of Dr. Gopinath of Department of Biotechnology and Dr. Mayank Goswami of Department of Physics on a project themed eye tumor detection using deep learning. This project eventually got awarded the Best BTP Award of the Year 2020 by Department of Biotechnology during the convocation of batch of 2020 held in November. In this video, I'll show how I commenced this project with the support provided by Dr. Mayank Goswami and his lab Divya Drishti, and how we achieved the results given the data that was provided. So here's the presentation.
All right. So a bit of an overview of the project. So in cancer research, there's a fundamental need of making the process of tumor visualization, quantification of its growth, more efficient, right? So make that possible, there's a need to automate the detection and segmentation of tumor, right? So this project essentially focuses on the same need. So the result of this project would try to form a baseline or a ground for a quick and more detailed diagnosis of cancer and its treatment. So a bit of a background on machine learning and deep learning. So what machine learning is, it's a branch of artificial intelligence that focuses on making machines understand how humans perceive and react to the surroundings, right? So this industry kind of tries to replicate the human way of getting an inference and recognizing patterns and making natural decisions. And this whole thing is fueled by the vast amount of data that is available in the world today. So data is available in vast amounts in every industry. Take it to be biotechnology, or take it to any other industry, maybe finance. Data is available in vast amounts, and that is kind of boosting the machine learning and deep learning concepts to disrupt these industries. So deep learning is further a subset of machine learning that uses neural networks to address the same need. So this project makes use of convolutional neural networks. So first thing, what are neural networks? All right, before moving on to the next slide, I'd like to emphasize on the fact that each image used in this presentation is either provided by Dr. Mayank and his lab. Those are the data images, or those are the depictory images are all created by me. So there won't be any sources apparent in the presentation. So, what are neural networks? Neural networks can be perceived to be a black box, which, when fed with an input image, which in our case would be an OCT image, um, give out on the other end an output, which in our case would be a mask, right? So this mask, when overlaid on the input image, the white region would superimpose on the tumor region in the input image, as you can see. What this black box consists of is a set of heavy, computationally heavy equations and transformatory matrices, which when are applied on the input layer, somehow transform the input into the output, which in our case both are images, right? So these set of equations are obtained after heavy amounts of training and after feeding in a lot of training data, which is provided by the provided for the project, right? So the whole uh, project was essentially finding these set of equations, right, through training. All right. So talking about data, I'd like to emphasize that all the data collected, all the data that has been used in this project was collected by Dr. Mayank Goswami and his team of researchers. For the purpose of it, 56 immunodeficient mouse eyes were injected with cancerous cells and evaluated for months. The images were visualized using fluorescent scanning, laser ophthalmoscopy, and volumetric optical coherent tomography. Again, I'd like to emphasize that all the data used in this project is owned and has been provided by Dr. Mayank and his lab. Uh, in case you want to understand how the data has been collected by Dr. Mayank, there's this research paper that I have referenced in this slide. So here are a few examples of what kind of images we have used in this project. So as you can see, in the first set of image, there's no apparent tumor in the input image. So hence, in the corresponding mask, there's no white region. But in the second set, you can see that there's a tumor present over here. and hence there's a white region of that when overlaid on the input image would directly superimpose on the tumor region, right? So on and so forth. There's a medium sized tumor example here, there's a relatively large sized tumor example over here. Right. The data that has been used for the project consisted of the left eye and right eye of 22 mice. Over a total of 7,000 images like those shown above were used. Along with that, the following data augmentation techniques were performed on data to increase the data, also the generalization. The data augmentation techniques included rotation, horizontal shift, width shift, zooming in and out, shearing, horizontal flip. I guess the names are self-explanatory. All right, moving on to the neural network architectures that were used. There were two DNN specifically which we used for this project. One being the traditional unit architecture, which is a famous architecture that is used widely in the biomedical image industry. And the second architecture that I have used is the multi-layer unit architecture, which was specifically designed by me, inspired from the unit itself, for this particular project. If you want to read more about unit architecture, I have referenced the right paper for it, where you can read about unit architecture. Okay, so the traditional unit architecture that we used was specifically of the as shown in the depiction over in the slide. So the input image is resized into a dimension of 128 cross 256 cross 3, 3 being the the channels R, G, and B, red, green, and blue. And as you can see, the first half of this unit architecture, it encodes the image into a very compact and dense matrix of size 4 cross 8 cross 256. As you can see uh, in the uh, in the green layer at the bottom. And so essentially the job of the encoding section of unit architecture is to you know just take the image as the input and give you a very compact and dense matrix, which in this case is 4 cross 8 cross 512, right? And this encoded matrix is then again decoded into a matrix by applying a specific set of operations and into a matrix of 128 cross 256 cross 16, as you can see in the blue line over here, right? And this a final to this a final convolutional operation is applied so that this matrix converts to a matrix two-dimensional matrix of 128 cross 256 cross 1, right? So this essentially represents our tumor mask, right? As you can see. So basically all the images were fed to this architecture and trained on as to receiving this kind of mask at the other end. So this was a traditional unit architecture. Here's the multi-layer unit architecture that I have designed, keeping the unit architecture as an inspiration. So as you can see in this, as the name suggests, multiple unit architectures are stacked together, right? So there's a unit architecture over here, there's a unit architecture over here, and so on and so forth. There are 5 unit architectures which are stacked together, right? So basically the operations are the same, the encoding and decoding, the concepts remain the same, but the thing is that many unit architectures are stacked together. Now, why I have done this? Basically, the reason is twofold, as I show here. So first reason is that it reduces the semantic gap between the encoder and decoder feature maps. So what I mean by this is, as you can see in the traditional unit architecture, the distance between the encoding subsequent matrix and the decoding subsequent matrix, the distance is too large, right? And it's large throughout. But in the multi-layer unit architecture, what I do is the gap between the first encoding encoding feature matrix and the the last decoding feature matrix, I fit in many channels in between so as to decrease the semantic gap between the the final matrices, right? So essentially this process decreases the semantic gap between the encoding feature vectors and the decoding feature vectors, right? And the second reason following the first reason is that if the feature maps are semantically similar, it's relatively easier for the optimizer to learn, learn the weights, right? So this, this argument can be, verified from the research paper which I have referenced in the slide below. So these are the two arguments which, hinted me that this architecture might perform better than the traditional unit architecture. Okay, so a bit about the factuals of the architectures and how the training was done. So in both the models, the input image was 128 cross 256 cross 3, 3 being the number of channels R, G, and B. The final encoded feature matrix was of dimension 4 cross 8 cross 512. The this encoded feature matrix is upscaled, is decoded to a matrix of dimension 128 cross 256 cross 16, which is in the end convolved into the output image, which is 128 cross 256 cross 1, which represents the mask. Right? So every downscaling step, downscaling means encoding. Every encoding or downscaling step is essentially a convolutional matrix of 3 cross 3, n being the number of kernels, followed by a dropout layer, and then again a convolutional layer, and then another max pooling layer, which essentially downscales the dimensions of the matrix representation. Every upscaling step is more or less the opposite of the downscaling step. It consists of a convolutional transpose operation of 2 cross 2 kernel, then concatenating with the subsequent feature matrix in the encoding region, and then another convolutional operation followed by a dropout, and then a final convolution for upscaling the image. Okay. For training, the whole training dataset was split in several subsets based on the size of tumors, which was small, medium, large, and mixed. So all the models obtained were tested on essentially two different testing sets, which are essentially one of them being the similar subset. For example, like if my training subset is consists of small tumors, then the testing subset would also consist of small tumors, and the other testing set was of mixed tumor sizes. For example, if my training subset consists of medium sized tumors, the mixed tumor sizes testing set would consist of small, medium, large, and mixed, every size of tumor, right? So yeah, so a total of two baseline experiments were done with the values of the all the hyperparameters kept at default. Right. So this was to form a baseline of what we should be improving on. Okay. So the optimizer that was used is Adam with a learning rate of 10 to the power minus 3. The loss that is used is binary cross entropy. The metrics for validation are used for are used as intersection over union and dice coefficient, and the models were trained consistently across 80 epochs throughout. Okay, moving on to the metrics that were used to validate the training of the performance of the model. So first is intersection over union, which is also called IOU. So intersection over union, it's basically as the name suggests, on the numerator, it's intersection of the predicted. It's the area of intersection of the predicted mask and the ground truth mask, and in the denominator it's the union of the same, right? So as can be inferred, uh, the more intersection over union is closer to one, the better our model is. Okay, so dice coefficient can be derived from intersection over union itself, with the equation being IOU is equal to dice upon 2 minus dice coefficient. I've linked, I've referenced the Medium article, which which can really explain what both the matrices are and how they work and why people use it. All right. So here are some details on on the training details of the biggest subset, which consisted of 3 to 29 training points and 9 to 2 validation data points, and consisted of mixed data. All right. So the as we can see over here, in the IOU and in the dice coefficient versus epochs, both the graphs are consistently increasing with an increasing slope towards the end, which is a good indication, telling us that if we increase the number of epochs further, the accuracy, the IOU and dice coefficients would increase, which is a really good thing to happen. And also, similarly, on the same lines, if we see loss versus epochs, we can see the loss is declining throughout consistently, which again tells us that if we increase the number of epochs, the loss will increase. The loss will decrease further. So that's a good indication. Okay, so here's a comparison of traditional unit architecture and multi-layer unit architecture, and with the statistics, the numbers, and so the data points basically tell us how many data points was the model trained on, and how many data points was the model validated on. All right, and it increases as we move down. As you can see, a multi-layer unit architecture maintains a consistent edge over the unit architecture as expected uh, throughout. Okay, this can be more visually seen in the graphs that I'll be showing in the subsequent slides. All right. Here's a slide depicting the accuracies versus training data points, the number of training data points. So as we can see in both the architectures, traditional unit architecture and multi-layer unit architecture, both the architectures, the performance in terms of IOU and dice coefficient increases as the number of training data points increase, right? And that's apparent in both the architectures more or less, right? So it's an indication that if we increase the number of data points, then um, our model performance will also increase, which is a hint for us on what to do for further experimentation. Okay, here's a comparison, as I told before, a comparison between the performances of unit and multi-layer unit. Okay, so the light red and the light blue colors depict the performance of multi-layer unit architecture, and as you can see that as the apart from the first experiment, which consisted of just 405 data points, which is not very significant. Apart from that, in every other experiment, multi-layer unit architecture has an edge, more or less, significant edge over uh, the unit architecture, which tells us that multi-layer unit architecture actually performs better than unit architecture when the number of training data points are significant. So it's a good thing to know. But however, we need to have more. We need to do more experiments to land to a final conclusion on which model is better and which gives us better results. All right. So finally, the results. Okay. So the first column shows the input image that was fed into the model after training. Here's the ground truth mask, which is the actual mask of the tumor region present in the input image. And finally, the results from the multi-layer unit architecture and the traditional unit model. All right, so as you can see, visually we cannot really see a lot of difference between. If we look closely, we can, of course, but from just skimming through the results, we can't really see that there's a much of a difference between the unit and multi-layer unit. But statistically speaking, as I showed before, multi-layer unit architecture performs slightly better than the unit architecture. Okay, so here are the results on the large size tumor images, and here are the results on relatively smaller sized tumor images. So as you can see in the third row over here, uh, the multi-layer unit architecture kind of uh, segments the tumor better than the unit architecture, as we can see, which is finding it hard to segment the smaller tumor over here. So it's another indication that the multi-layer unit architecture is slightly better. All right. So I do have some more results to show, and it's really exciting because those will be video depictions. So here we go. All right. So in this video, we'll see that as the tumor emerges, in the feed, the model actually superimposes a mask on the top of the tumor, right? So it's a really good result and really good to see this thing. and this happens all in real time. So, all right. So going back to the presentation. Okay, so the future workflow for this thing would be like we inferred in the previous slides on what should be working on. Like we just performed experiments on using constant set of hyperparameters. The future workflow would be to tune the hyperparameters more efficiently so that the models perform better and better and better, and train with more data, and and increase the epochs as well to see what works best for us. Okay, so other than that, we'll be trying to uh, output some reports, some inferences out of this out of uh, the automated segmentation from the tumors, reports like how fast is the tumor growing, or how what's the area of the tumor, etc. So the this project can also be expanded to other body parts, other tumors in other regions of the body, apart from just the eye. If more data is provided, similar architectures can be used to test it on the other kind of images, OCT, CT scan images. All right. And maybe we can also build an application that takes the OCT scan image of infected organs and output a real-time diagnosis and treatment report. And but that's something that needs a lot of work, and would really need some heavy work. Right. So that was my presentation, and that was my project. Thank you for listening to me and having your attention.